Okay, guys, welcome to Big Idea 6 AP review. We're going to go through and talk about thermochemistry. My page has color. Sorry if you guys doesn't. You're welcome to print the one out with color, but yeah, mine's got color and yours doesn't. Sorry about that. So let's start over here on the left and we'll work our way down. Go through these kind of quickly here. The first two little graphs right here, we did talk a little bit about in kinetics, but looking at this potential energy diagram, you've got kind of the reaction progression on the bottom down here. This is meaning starting at the beginning and going to the end. And then potential energy is over here on the left-hand side. There is a certain amount of energy that is necessary for reactions to occur. That is that activation energy right here. That is usually denoted by E sub A as your activation energy. If you look at these two different graphs, they have two different activation energies. Actually, one looks like it's forward and one looks like it's reverse of the same reaction, but it doesn't really make any difference. The one on the left is going to be exothermic. So this is going to have a negative delta H reaction, heat of reaction, and the other is going to have a positive delta H or heat of reaction. You can see that from here to here, where it says energy absorbed, and from this point down here to this point up here is going to be your delta H. Remember that you always take products minus reactants, and we'll visit this again in a little bit. But those are the different graphs and kind of what they're going to look like. Reactants will start on the left-hand side, products on the right. You could see these asked in terms of a reverse reaction, which would mean you just go this direction. So this one is an exothermic reaction in the forward reaction, but it is an endothermic reaction in reverse, which you would flip your delta H's anyway. But essentially, that's what's going on here. Those are your endo and exothermic reactions. The endothermic reaction is actually going to take energy from the surroundings and it's going to go to the system. So this would be energy into the system, means that it is endothermic, right? If it's exiting the system, it's exothermic. The system is actually going to donate energy to the surroundings. So this would be energy exiting or exo of the system. Okay, that's it. Simple kind of ways to memorize them or whatever. I'm sure you have your own, but yeah, same kind of deal. If we go down here to the bottom, and we're going to talk about all the different ways to calculate delta H here in a little bit. If we go down here on the bottom, here we've got a heat of solution. So you've got a certain delta H value that is a certain amount of energy that is required to actually separate the pieces of the solvent, and a certain amount of energy that is required to separate the solute. And so once they're separated, those two would come together to give you a heat of solution. And this heat of solution is generally the amount of energy that's released as they interact. So this is the energy that's released as the solution is formed, or as the solute and solvent react with each other. Solvent, yeah. So as those two get together, they actually produce an energy of solution. Now we looked at these in class, not really on a molecular level like this, but in kind of a chart. And I'll kind of draw one off down here on the bottom. Don't have one here on this, but you had a certain amount of energy that was necessary to like separate your solvent and your solute, and this may ring some bells here. And then as they came back together, there was energy for the solution. So this is for the solution. I spelled that wrong. Look at me. I just issues. Thanks, guys. Solution. And then over here would be either your solvent or your solute, whatever. You add those two together and it comes. If this number here is higher or lower here, your delta H for the reaction in this case would be positive. It'd be endothermic. But if in fact that value carried below this, then that would mean that energy was actually given off in the formation of the solution, which is typically true, but it depends. It depends. So anyway, that's kind of how we saw them and worked them in the homework, but this is just showing you on a molecular level what's happening as you separate them. It takes an amount of energy, and then once they come together, they release a certain amount of energy. So like I said, that dissolving can be endo or exothermic. If we look at it here, if these two are going to be greater, it's going to be positive. If these two are going to be less than what it is, then it's going to be, or less than the solution formation heat, it's going to be negative. So down here on the bottom, actually, let's go over this way. So over here, heat is always going to flow from a lower system or amount of heat to something that is something that contains a greater amount of energy to something with a lower amount of energy. They're always going to move from a hotter object to a colder object. And so the heat flow in this direction would be in this direction. And then they would equalize that heat if they sit next to each other. Now, there's a lot of things that actually play into this in terms of how much heat would be absorbed by each object. You would need to look at their specific heat values and such, how much energy is actually being given. But as a simple kind of how it works is that heat will always flow from energy, an object of higher energy to an object of lower energy. So always moving from, that's an eraser, always moving from hot to cold until, of course, they reach thermal equilibrium where they're both the same. Okay, so if I come over down here, it says, when substances are heated, they experience phase changes. That's true. This could be graphical. And if you were given a question that asks, and of course we did quite a bit of this, as you know, in advanced chem as well as in AP. But if you're given a certain substance and you want to find out how much energy is released or gained when something takes place, and the object starts at one temperature and ends at another temperature, you would need to draw a phase change graph like this, or a heat curve is what they're called. So if, say, ice was down here at -20, and I wanted to change to steam at 130 degrees, yeah, it's actually going to be a 5-step problem. You'd have one step here, another step, another step, another step, another step. If I were working these, would label them kind of as I am doing now. I would label this step here 1, this step here where there's a phase change 2, and then 3 along the curve here, 4 on the phase change there, and 5 up top as the steam is heated if this were ice, or as the gas is heated if it were something else. During that phase change, notice that the temperature stays the same. You would use dimensional analysis to solve those problems. When there is a temperature change, though, you'll actually use Q equals MC delta T. That C value will change depending on what state of matter it's in. If it is a liquid, like if we're using water for an example, water is a liquid, 4.18 joules per gram degree C, whereas the specific heat of ice is 2.1 and that of steam is 2.0. Those numbers will be given to you on your AP exam, I'm certain. But it doesn't have to be water. They could give you something else. You could be heating ethanol or benzene or whatever. But if they do, they'll certainly give you those numbers, and they're calculated the exact same way. Be careful with tricky stuff where they give you, say, you have, 2 ice cubes that you're melting, and each has a mass of. Make sure that you multiply that by 2. It would be silly for them to do that, but we did, so you never really know. So let's go back up to the top here and go with all those delta H's. Several different ways to calculate them, and we'll just kind of review those different ways here. So calorimetry is where an object, you measure the specific heat of an object or quantify it by putting it in water. And you use what's called a calorimeter, which is something that minimalizes the heat loss to the surroundings, like a coffee cup. So calorimetry uses that transfer of energy to calculate what the specific heat is. And usually it's between 2 different substances. What you'll be using is Q equals MC delta T. For these, you can use degrees Celsius, absolutely. If they give you the specific heat, though, in kelvins, you can use kelvins. Since it's going to be a difference of the 2, it's not really going to matter. The 273 is going to fall out. If something is a negative Q value, it means that heat is actually released. It will mean positive delta H, and positive Q means negative delta H, but it's if the amount of energy is actually gained by the system or gained by the surroundings is what this is actually trying to tell you. So I have my coffee cup over here. I'm looking at this over here. I've got my coffee cup and my system is down here, and my surroundings actually is kind of the thermometer or the water, right? And so the thermometer is part of the surroundings. So if the thermometer is gaining energy and becoming positive, it means that it gained energy from the system. So this delta H is the system, and this Q is a measurement of the surroundings. So that's why these two are opposite. Now, if you're trying to find out if something is released energy and you calculate the Q value and it gives you a negative Q, the delta H is negative. But in calorimetry, it's switched because you cannot measure the system. You actually measure how much energy is gained or lost by the surroundings. So those two systems could be two systems added together. And in that case, that would be a little bit different. You would have to calculate the delta H using the mass of the limiting reagent instead of, you would have to check and see if you've got the same number of moles of both and how they react together. But that would be, for instance, if you add HCl and NaOH together and then measure, that would be different than just putting, a solid in water and transferring that energy. A heat solid placed in water like there, doing an MCAT equals MCAT is the way to do it, I think. Be careful though when you have your temperature differences, because one of them will have to be flipped. You can do it as Q for one will equal the negative Q for the other. And then you could actually use T final minus T initial to solve them. If you do it in terms of Q equals Q, then you have to kind of play with your delta T's there, or just use absolute value of your delta T's. The greater an object's heat capacity, in other words, it's specific heat capacity sometimes, but it's heat capacity, the more energy is actually needed to change its temperature. So if something has a really high heat capacity, it can actually absorb and hold quite a bit more energy. And so it will actually need a greater amount of energy to change that. Something with really low specific heat or low heat capacity changes temperature very easily. Water has a high heat capacity and a high specific heat capacity. It's 1.00 calories per gram degree C, whereas, or joules, it's 4.18 joules per gram degree C in specific heat. If you looked at something like lead or silicon or another metal perhaps, they tend to have much lower specific heats and can transfer energy very readily. If you heat up a pan, it doesn't take nearly as long to heat a metal pan as it does a cup or the same mass of boiling water because of that difference in specific heat values. So if we go down here, during a chemical reaction, energy is put into the reactants, to break the bonds. And the delta H can be found by doing essentially your bonds broken minus your bonds formed. So we've got an example, and this is one way to calculate delta H. And it's the only time where you're doing things that are reactants minus things that are products. So bonds broken are the bonds broken in the reactants to produce the bonds that are formed that are on the product side. So if I do ethene is C2H4. Got H here and H here. This is really terrible drawing it this small, but that's okay. There's a double bond between the two. Reacts with hydrobromic acid, which would just be HBr. And it produces, and I do HBr. Let me put all my dots on there. It'd be perfect. And then it produces bromoethane, which would just be a single bond between the carbon atoms. Hydrogen's coming off all the way around. Yeah, and then a bromine on one of the carbons. Doesn't really matter which one or where, but there you go. To do this, you'll break all the bonds of the reactants and break all the bonds of the products. You don't necessarily have to do that. You could just break the ones that are breaking and forming and not all of them. I would do all of them. It's just easier. So my delta H value is going to equal, and I break all of the bonds inside here. So I'm going to break this one and break this one and break this one and break this one. All those carbon hydrogen bonds are the same. There are 4 of them, and each of them listed in the chart over here are 414. I think that's kilojoules per mole. Yeah. And then the other ones I'm going to break is the carbon-carbon bond between them, which there is one, which is 615. And then I am going to add to it the break of the hydrogen bromine bond, which is 368. All of those would be all the bonds that are broken on the reactant side, minus all the bonds that are formed on the product. And over here I've got 5, all of the carbon hydrogen bonds, again, 5 times that same 414, plus 347, plus, and I do that last one is 276, the one for the carbon The one, excuse me, for the that carbon bromine. My bad. There we go. If I go and I calculate these, I end up getting negative 54 kilojoules per mole. And this would represent my delta H for this reaction. So then I could say, oh, it's exothermic. There are other ways to calculate it, but this one always comes up every year, and students typically don't do well on it, unfortunately, and it's actually pretty easy. They'll give you a chart of bond enthalpies, and if they do give you bond enthalpies, you'll need to break all of your reactant bonds minus break all your product bonds and solve. So it's bonds broken on the reactant side minus the bonds that are formed on your product side. So if we go over down here, instead of the bond enthalpies of reactants and products are known, delta H can be found by doing, now these are enthalpies of formation, not bond enthalpies. So this is the amount of energy that was gained or released when the substance was made from its elements. And sometimes students kind of miss that. So O2 here would be oxygen combining with another oxygen to produce O2. That doesn't require any energy, and it just naturally happens. And so that's why that bond enthalpy is actually 0. For the ammonia though, and you guys don't have to write this down, I'm just explaining really quickly, but nitrogen would combine with hydrogen, probably like this, to produce NH3. And if I were to solve for this bond enthalpy for 1 mole of ammonia, it would, now that's not balanced, I know, but if it were for 1 mole of ammonia, it would release 46 kilojoules of energy. Now you could calculate this using bonds broken minus bonds formed and solve for that value had they given you those values. But we're not going to do that. We're going to look up on a chart and see what those heats of formation values are. You'll see heats of formation labeled with that F at the bottom. So if it says delta H naught with an F, it means the value that it is to form the ammonia. In this case, what you do instead of taking bonds broken minus bonds formed is you take the delta H value for your products minus the delta H value for your reactants. Then you'll find out how much is left over as a product. If that value is negative, it's exothermic. If that value is positive, it would be endothermic. So if I go ahead and do it for this one, I've got my delta H naught F for the reactions. Oh, let me say, this is not for heat of formation. This is for the entire reaction. Yeah. Is going to be 4 times my value for the nitrogen monoxide, which is 90, plus 6 times my negative 242, which I think is my water. That's correct. Minus the 4 times my ammonia value, which is negative 46. Plus 5 times my oxygen value, which is 0. Didn't necessarily have to do that. And what I end up getting over here is negative 908 kilojoules per mole. Demonstrating, okay, that this reaction entirely gives off 908 kilojoules per mole of the reaction as it's written. So for 4 moles of ammonia, when this happens, it's going to give off 908 kilojoules per mole of the reaction, or per 4 moles of ammonia, not per 1 mole of it. So when it says delta H for the reaction, be careful that because that's per mole of the reaction as it's written. And you can use mole-mole ratios to figure out what it is for others or each or whatever, it's fine. The other way to do it, or the last way to do it, is using Hess's law. So, and I really like Hess's law. Hess's law is kind of puzzle-esque and figuring it out stuff. I really enjoy that. But here we've got, given the following reactions and some delta H naught values for each reaction, it says determine the heat of reaction in kilojoules for this. And they've given me all 3 of these. And so what I have to do is kind of figure out what's going on and how to arrange them. So if I look, I need to, the way I do it, and you may have your own specific way of doing it, but I look for things that are already correct on the right side. So I've got B2H6 there, and I also, and that's my goal equation. This is kind of my goal, what I'm trying to get at the end. So I'm given that B2H6 is on the reactant side, and on that one, it's on the reactant side, which is good. And so I probably don't need to change that one, and I may have to later. But what I'm going to do is go ahead and write it like it is, and then I'll change it later because I don't have to do anything with it. Some of you like to skip this step, but I don't recommend that. I would write out the reactions every time. So H3, BO3 plus 6H2, and my delta H for that part is negative 493.4 kilojoules per mole. Okay. If I, let's go further. So let's look at, say, the Cl2. The Cl2 I've got in this reaction right here, right? And in that reaction right there, I've only got half a mole of Cl2, but I need quite a bit more of it. In fact, I need 6 moles of it if I look up at my reaction. So I need 6. So I'm probably going to have to multiply that by 12. So let's just go ahead and give that a shot. Let's just go ahead and multiply this whole thing here by 12. So if I do that, I would have 6 moles of the H2 plus 6 moles of the Cl2 are going to give me 12 moles of HCl. And what I would do to the delta H value is the same. So delta H would be 12 times the negative 92.3. Okay. The last thing I'm missing is the H3BO3. Not H3BO3, sorry, I'm looking at that one for sure, but is the hydrochloric acid. I'm missing a hydrochloric acid and the BCl3. So if I look here, I've got the hydrochloric acid here, and I've got my BCl3 here. I've also got HCl down there on the bottom. I need 6 of them. I already have 12 of them. So this is interesting. Probably I'm going to have to flip this one and put that BCl3 as a product because I don't have it as a product, and I need to cancel out some of those 12. So this one will move over to the other side and this will move over to this side if I flip it. Problem is that I need a coefficient of 2 with my BCl3. So I'm going to go ahead and multiply that through by 2 and see what happens. So what I'm doing essentially is I am reversing this first reaction and multiplying it by essentially a -2 or a 2. I am going to do the -2 when I do the delta H. Let's go ahead and write that down, save myself some time. So I have -2 times my -112.5. And if I flip that and multiply it by 2, I'm going to get 2 of the H3BO3. I am also going to get 6 moles of the HCl. And now I'm going over to my reactant side up here, end up with 2 BCl3, which is what I'm looking for anyway, and my 6 moles of H2O. So now I'm going to go through and look at the things that cancel. So I've written all my delta H values there, and I would just add those up if I actually get my goal equation. So let's check. Let's see what cancels. I've got 6 moles of water they're going to cancel. I also have 6 moles of HCl here, and then this would also become 6. The 6 moles of hydrogen is going to cancel from both. This H3BO3 is gone. And I think that's it. So I have B2H6 plus my 6 moles of chlorine, yielding this 2 moles of BCl3 and 6 moles of the hydrochloric acid. If I go check that with my goal equation up at the top, do I have the same equation? B2H6, I do. Oh, hey, okay. If I get out my calculator and I add these up, I end up getting that my delta H value for the entire reaction is -1376 kilojoules per mole of reaction. There you go. That's kind of fast. I don't know what's going on there. Sorry about that. So yeah, that was the last way to actually calculate delta H. We'll revisit and do delta H again when we see free energy and electrochem, probably in, let's see, that would be big idea 9. But yeah, so that closes off the thermochem, a little quick review of thermochem. If you have questions, talk to your instructor, and I'll see you in the next unit for equilibrium.